Hi, my name is Andrea Legrand, and today we are going to be talking about a specific system, and we are going to be discussing with a flow rate coming in and a flow rate coming out, changes in height, temperature, and concentration with respect to time. So in order to explain exactly what's going to happen, I'm going to draw our system. So we're going to have a specific container, volume, that has a cross-sectional area right down here. Say it's a cylinder per se. Doesn't really matter. We're not going to be deriving the area. This is just putting in our numbers, all right? And then we're going to have this water in here that is being constantly stirred, like if you were in chemistry and you had a stir bar at the bottom of your beaker with a stir plate. And that is allowing for a consistent temperature throughout the system, as well as whenever we're going to deal with concentration, a consistent concentration throughout the system. All right, and so the height is the height of the liquid right there. In this case, let's just say it's water. And there is a flow rate coming in, and that is going to be used with the variable Q. So that is our flow rate in. And then we have a rate coming out, which we're going to do Q out. And in this specific situation, we are given that the Q out is equal to alpha height of 1/2. And so this alpha in our specific case is going to be 0.4, but I'm leaving it as a variable, so this can be used with any specific numerical variable, all right? And so with this system, we have that the area is equal to 1 meters squared. Our initial temperature, so that's going to be T naught, that is going to be 300. Our temperature coming in is going to be 320. Our initial height is going to be 1, and our rate coming in, I believe, is, sorry, I'm just pulling up the numbers. It is 1 meter per second. That's what I thought it was, but I wanted to double check. All right, so 1, you okay, buddy? Sorry, my guinea pig's being loud. Kilograms, well, I don't remember. All right, so this is our system, and we are going to begin talking about this with the change in height. So with this particular system, there is a constant changing of the mass within the container. And so this is going to be our dm, all right? And so we have the mass coming in, and we also have the mass coming out. So that is going to be, it is equal to coming in and the change of the mass coming out, all right? And so with this, we can adjust it because our mass, as far as inside, that is going to be the change in the density times the area times the height, because the mass is equal to the volume times the density, and the volume is the area times the height. So that's what that is right there. And so that is going to be equal to, and in this case, our mass coming in is going to be our density times the flow rate coming in, all right? And then our change in mass coming out is going to be the same thing, but we were given that our rate coming out is the alpha h square root or to the 1/2. So we're going to put that in because that's just going to make our life easier in the future. So we have this. Well, these two things are constant, right? So we can pull those out of the derivative. And with that, the the densities are all going to cancel because it's all the same density. This is just with one type of molecule within the system, right? So in this case, it's going to be H2O molecules. All right, so that's going to give us our our area can come out, H over dt is equal to our rate coming in minus alpha times H to the 1/2. And then we can take out this A right here. Let me just erase that. And then bring it, divide it. So now, right there, that is our correlation between the change of height over time. Okay? So I'm going to keep that right there. I believe you can see that. So what I'm going to do now is we are going to do the change of the temperature over time. So remember, the rate coming in, that has a different temperature than the system, okay? And, well, in this case, it's going to have to deal with some energy, right? We're going to do more of a change in mass times energy, right? So for this case, let me just put a nice little line right here, block that off. We're going to have the change in the mass, and this is the energy of the system plus the kinetic energy plus the potential energy is equal to the change, here, because both of these are multiplied by the enthalpy, which is represented by H. Let me just write that down just to help us out in the future, because I tend to forget what we put variables as. So we're going to do that, and that is plus kinetic energy plus potential energy. All of that is multiplied by our change in M in minus our change in M out. A little tight there. And so in this system, we're going to have that our change in our kinetic energy and potential energy, that's going to be negligible. So that means that with this, it's just going to be our dmu system is equal to H of the change in mass coming in minus H change of mass coming out. Okay? And so with this, we know that in this specific system that the following items are true, okay? And that is that let me write it up here, that the change in the enthalpy is, our change in the enthalpy is equal to the Cp times the change in time. And then we also know that in this system, because it's a liquid, that our change in the energy of the system, that is going to be our specific heat times the change in time. And so, well, we can plug that in, right? So let's do that. And with this, we'll switch the M's to be what they were in here, because we're going to want to combine these, right? To make life easier for us in the future. So we have our D times, and remember that in all of these cases, the density cancels out because it's all the same density, right? So I am going to save ourselves some space, and I'm not going to write down the density, but just know that it's there before they all cancel out. So we're going to have that times the area times the height times, and that is all over dt. And then our change of U in the system, that comes out of the D area, and that is multiplied by our CV change in time, right? And so that is going to be equal to, both of these are going to be multiplied by CV. Well, this is, so this one's CP, change in time. is going to be multiplied by our flow rate coming in minus our alpha h to the 1/2. All right? And so in this specific situation, based on the fact that it's a liquid and we're just going to have this, is that our Cp is going to be equal to Cv. Okay? So that means that those are going to cancel. But before we do that, we want to talk about something else. Another way we can write the change in the energy, right? And this is the same for the change in the heat. So we have two dTs, right? And so that means that the U of a specific temperature minus the energy at a reference point, because that's a change, is equal to Cv times temperature minus temperature at a reference point, okay? And so what we're going to do now is we're going to plug that in. So instead of having that dt right there, that's how we're going to adjust it, all right? And so that means I am going to move this square because I'm going to need some more space to write. So that means that we have, because the area pulls out, I'm just going to make life easier. So the area times the Cv, which is T minus T ref, and then dH over dt is equal to, and we have our Cp, T minus T ref, times our rate coming in minus alpha h to the 1/2. So now when you're looking at this, you're like, that's a lot of t's. But in this case, what we're going to do is, well, let's just think about it. So our t reference, that can be any point that we determine, right? And so, well, that's a constant. Therefore, all of those values cancel out, right? So that means that we can take these all out, right? And so what that's going to do is that is going to leave us with this just multiplied by t. Well, you know what we talked about a little bit earlier? That our Cp is equal to Cv. Well, those can also cancel out, right? So let's go boom, boom, and I think that's it. And that leaves us with our area times dH over dt is equal to our temperature times our rate coming in minus alpha h to the 1/2. And so now we want to get, oh wait, I forgot the t right here. Sorry. Okay, so now we want to get it by itself, okay? And so, sorry, the t needs to be over here. We want to get that change of temperature by itself, okay? Well, we'll divide out the a to get it over here. And, well, we can separate that, right? So that's going to be our h times the change of time, temperature over time, plus our temperature times the change in height over time, which that is equal to our temperature times the flow rate in minus our temperature times alpha h to the 1/2 all over our area. And so now what we can do is we can move this over here. Well, not that one. Whoops. I'm going to move this one over there by subtraction. And then we can divide out h, right? So that's going to give us d of t over d of t. So change in temperature over change in time is going to be equal to, in parentheses, temperature times the rate coming in minus the temperature alpha h to the 1/2 all over our A minus temperature change in height all multiplied by 1 over h. And so this right here is our correlation between the change of temperature over time for this system up here. And in this case, when you're looking at it, well, this is the temperature coming in, right? So this is going to end up being our T in. So what we're going to do now is we are going to take this and we are going to code it in Python, aka Google Colaboratory. Okay, so now we are going to take what we just did and we are going to code it in Python. So I've already put in NumPy and brought in the integration code and how we can put in subplots. So that's just what all this is. Didn't want you to have to sit through me typing that. So first thing we're going to do is we're going to put in all of our initial values. So our initial area is equal to 1. And so I'm making sure to put the dot behind the 1 because otherwise it'll think that it's an integer and that it can't produce anything with decimals. It's a weird system. And so our initial height is also 1, and then our initial temperature is 300 Kelvin. Our temperature of what's coming in is 320. And then we have our flow rate coming in, that is also 1. Our value of alpha is 0.4. And we are going to run this until T final, which I'm going to put in as TF. And that is going to be until 100 seconds. All right. Shift enter, that's the easiest thing I'll be typing today. So what we're going to do now is we're going to put in our function, which we're going to put in our definition, and that is going to be t comma k. And make sure I put that semicolon there. I like to forget the semicolon. And so now what we're going to do is put in our h comma t, that is equal to our k value. So that's just saying that our k value, which is our dependent variable, is going to be the h and t, where our t is the independent variable. Okay, and so now we're going to type in the equations that we just determined on the whiteboard. And so this is where things can get a little bit messy as far as typing goes. So this one is going to be the change in height is equal to the flow rate in minus alpha times the height to the power of, in parentheses, put the 1/2, otherwise it won't be taking the square root, it'll be taking it to the power of 1 and then dividing it all by 2, because, you know, Python is very specific about how you type everything. It's all going to be divided by the area. No, not alpha. The area. Thank you. All right, and so you're changing temperature now, and this is where I tend to forget some parentheses. Okay, so take a deep breath. There's going to be a lot of letters. All right, so we're starting with our temperature times our flow rate in, subtracted by our temperature times that alpha times our h to the power of that 1/2, and then close that parentheses, divided by the area, and then that is going to be subtracted by our temperature times our change in height, and all of that is going to be divided by the height. Alright, and so to finish that out, we are going to put what we want it to return, and we're going to want it to return an array. So np.array of our dh comma dt, with the t capitalized, not the d. And that should be good. Alrighty, let me scroll down some. And so now what we're going to do is we are going to use that code that we imported for integrating, and we are going to make a system so that we can get our integrated values and get our h and t values for specific time frames. So with that, we're going to put our solution is equal to solve underscore IVP. And that is going to be in parentheses. Put in our function. We're going to put in our starting x values, which is going to be from 0 to t final. And then we put in our np.array, and that's going to start from our initial height and then our initial temperature. That should be good. I need to make sure, because I've made this mistake before, that this is also in parentheses. All right, now we put in our method. This is just specific, is rado, and then our dense underscore output is equal to true. And close that parentheses, put dot solution. And not let the system complete your sentence without understanding what you're doing. So now what we're going to put in is we're going to set the parameters for what our t-plot. So this is our temperature plotting. So our temperature plotting is going to be an array that we're going to put linspace. Our initial value is 0, and then it's going to go to our t-final, and then let's say space it 300. So this is going to create an array of 300 values ranging from 0 to our t-final, which happens to be 100. And so with that, we are going to put our h and our t is equal to the solution plugging in those t-plot values. So that's going to allow us to get the values of the h and t for each time that is in the t-plot that we created. All right, and so from here we are going to put in our graph. So this is the final moment to see if what we've been doing has worked. And so we're going to be doing 2 figures. And so to start, we're going to go fig is equal to make underscore subplots. And then we're going to put in rows. And so we're going to have 1 row. And then this is how we're going to make 2 specific plots, and we're going to put at 2 under columns. So now we're going to put fig dot add underscore scatter. And so our x is going to be t-plot. Our y, for the first one, we're going to have that be our height. And then we are going, sorry, it's getting late. And this information is coming from row is equal to 1, column is equal to 1. And so for the second one, we're going to do the exact same thing, just changing 2 parts of it. So our x is equal to t-plot, same thing. Our y in this case is going to be equal to the temperature. Our row is the exact same thing, but our column is going to be equal to 2. So this is making sure that it's our second column. So that should give us 2 separate plots. Where did I forget? Oh, I've done this before. So this is our t initial. All right, and so now when I go shift enter, shift enter, shift enter, there we go. I have made that mistake in a previous recording that the sound messed up on. So here is our 2 plots. The one in blue is our change in height with respect to time, and the one in red is our change in temperature with respect to time. So now we are going to talk about the change in concentration of this system rather than the change of time. And so we're going to go back to the whiteboard, and then you'll be coming back here with this version of me to finish coding in Python. So now we are going to talk about concentration. So in this case, the temperature is staying consistent, but with the flow rate coming in, that flow has a different concentration than what's in the system. So that means we need 2 more values, okay? So I'm going to write that down real quick, and we are given that. So the concentration, personally, I'm going to do M because I'm a chemistry person, and my brain thinks, oh, molarity. So that's just a personal thing. You can use C, you can use something else. This is just what I do. So the M for me is going to be concentration, the capitalized M. And so our M coming in, let me check what that value is. I'm pretty sure it's just 1. Yep, it is. All right, our concentration coming in is 1 kilogram per meter cubed. And then our initial concentration within the system, so that's going to be M naught, is 0.1 kilograms per meters cubed. So let's say like maybe it's like water and peroxide. So this is just what that is. But in this case, we want to keep that change in height equation because it worked before, we want it to work here. So in this situation, we're going to say that the density of the system is equal to the density in, which is equal to the density out. And so that is just making it so that we can use this equation from before. Okay? And, well, let's go back to our system. The system has a stir bar in it. And so that means that it is consistent throughout. And that allows us to know that our concentration coming out is equal to our concentration of the system. Okay, so let's create this equation. So let's start with the same thing that we've always started with. That is our change in our mass of the system is equal to our change in mass coming in minus our change in mass coming out. And, well, let's separate that, right? So go back to how we know, well, we said that our change in our density times area times height. Our mass can be written as well as our concentration times the area times the height. Obviously, this is all over change in time. And so we can do that exact same thing because the density, as far as the density is equal to the mass per cubed unit. And so with this, well, isn't our concentration just mass per volume? So we can kind of alternate that, right? So with that, we are going to put in that this is our concentration coming in times our flow rate coming in, subtracted by our concentration going out, which is the same as concentration of the system, times our alpha times height to the 1/2. And so as before, our area is constant, so we can take that out, divide it over. And so we're going to do the exact same thing as we did before, okay? So once that area comes out, moves it over here, well, that's you having to separate this out, right? So that's just our H change in concentration over change in time plus our concentration change in height over change in time is equal to our concentration in times flow rate in minus our concentration times alpha times height over our area. And so we're going to do the same thing as we did before. You'll notice this, once we finish it out, it is almost identical. So that means that we're going to pull this over here and we're going to divide it out by H. So our change in concentration over our change in time, that is going to be equal to our change in concentration coming in with our rate coming in, subtracted by our concentration times alpha times the height to the 1/2 over our area, subtracted by our concentration times the change in height, all of that divided by H. So this right here is our correlation between the change in concentration of the system over time. If you notice, everything is the exact same thing as up here for our change in temperature over time, except for T's have changed to M's, or C's if you choose to use C's as your concentration. And so, well, I think our Python's going to be a little bit easier this time, so let's go ahead and go do that. All right, so back to Python. So what we just learned is that the change in concentration with respect to time is in a very similar equation, pretty much almost identical equation to the change in temperature. And so why waste all of our hard work, you know? If we made mistakes in typing, we already fixed them. We know that this code works. So let's save some time. All right. So we're going to put in our constants first, but actually this is a personal thing that I like to do. I'm going to put in our concentration versus time just because I want to remember what each section is. All right. So we're going to go, our initial concentration of the system is 0.1 kilograms per meter cubed, and that our concentration coming in is that 1 kilogram per meters cubed. All right? And so we're going to make life easy, right? I'm just going to take what's up here, and I'm going to copy it, and I'm going to paste it, and I'm going to change every single capitalized T that I can find into an M. All right? Because that's the only difference between the two equations, as we have discovered on our whiteboard. And so that should be good. And now we're going to do the exact same thing for the next two things. All right, and so we need our M. M. All right, and here's the moment of truth, which we're almost positive that it'll work out because it already worked before. All right. There we are. So if you see the concentration versus time right over here, it looks very similar to both of those graphs, which is going to, it's just the numbers are a bit different up here. All right, so if you see with this, we talked about how with this one, we said that our temperature was going to end, well, our temperature coming in was to 320 Kelvin, right? So that means our system can't get any warmer than 320. And so once a certain amount of it comes in, it's just going to cap off like that. That's why it is leveling off. And so it's the same thing with down here. Our concentration of one thing can't really get more than 1 in this case. So that has been talking about the correlation with flow over time, with talking about change in height, in temperature, and concentration, and graphing it within Python. So thank you guys so much for watching.